Alright, it's time for us to tackle piecewise functions. On the screen you see 6 examples of piecewise functions. You can see that they're literally created from several different functions. A lot of times it's going to be 2 or 3 functions. It could be more though, but this one, for example, sort of swings down here, has an open circle, jumps up here, and is linear. So that's made up of 2 pieces, and there's this nice little barrier here for the left and right sides. Alright, what you're looking at here is the absolute value function written as a piecewise function, and you can see that there are these constraints here. When x is greater than or equal to 0, it's defined that way, and when x is less than 0, it's defined this way. And right here we have, again, 2 pieces. We have a parabola that stops there, jumps down here, and the function picks back up as a constant function there. Down here we have 2 pieces as well. There's a disconnect right here. Here we have the disconnect where there's actually no function value at 0. Here we have, looks like 1, 2, 3, 4 pieces on this piecewise function. This one's pretty tricky. So we are going to study these, learn how to graph them, and talk about their domains and ranges and things. So here we go. First one. We have 2 linear pieces. The top section I'm going to graph in red, and the bottom section I'll graph in green. This -2, these are what we call, of course, our constraints, right? And our constraints are basically, that's sort of our roadmap to tell us where each function starts and stops. And we're talking -2, so that usually means that there's going to be some sort of barrier here at -2. Now you don't have to draw a dotted line, but you can. And there are 2 schools of thought on how to graph these things. I'm going to show you my favorite way. I might mention the other way, but the way that I graph these is I set up my 2 sort of tables of values, and I say, alright, the top function is in red, and it defines the function when all the domain values are less than -2. So less than -2, that means like -6, -5, -4, and -3. So let's define those values. We're going to be looking at the top function. So when x is -6, you plug that in. -6 plus 5 is -1. This is 0. This is +1, and this is +2. Now, it's important to also get an idea of what the graph's going to do, what the top graph is going to do at -2. So when you plug -2 in here, you get +3. +3. I'm going to put a star next to that because it's not actually a point on the red graph, but it's worth knowing. So before we go to the green, let's plot those red points over here. -6, -1, 1, 2, 3, 4, 5, 6 -1s over here. -5, comma 0, 1, 2, 3, 4, 5. -4, -1, excuse me, +1. And -3, +2. Now this open circle at -2, comma 3, I'm going to put right there. Put a nice open circle because the graph is not actually defined there. I know that this is linear, so I'm just going to connect these dots, and I am good to go. The green function is defined when x is greater than or equal to -2. So -2, -1, 0, and 1. At -2, I'm using the bottom function now. Plug that in, you get +4 minus 1, which is 3. Plug -1 in that green function, and you get +1. Plug 0 in, you get -1. Plug 1 in, you get -3. So plot those. These are all closed dots. -2, 3. Well, that happens to reside right on the other one, so I'll fill that in. -1, 1, 0, -1, and 1, -3. So again, these are linear, so I'm just going to connect these dots the best I can with a line that's fairly straight. If you're at home, just use a ruler to make sure that everything looks kind of good. I can't use a ruler on here though. So what I have is two pieces, the red and the green, that they come together. They're not always going to come together. In fact, a lot of times they're not going to. And to the left of this wall, if you will, this imaginary wall here, to the left of that it's defined by the red, and to the right of that it's defined by the green. This is a continuous function. There's no break at all. So we call that continuous. And it has a maximum value. The maximum value here is -2, 3. That's defined by the green function, not the red. The domain of this would be everything, from -infinity to +infinity. The range, on the other hand, is not everything because it stops. It goes from -infinity all the way up to +3. I'll close that off with a bracket because of the green value at -2, 3. So there you go. There's your first example. Might have been a little confusing, so let's do a couple more. Next one, let's use blue and brown. In the blue function, it's defined, the function is defined when x is greater than or equal to 1. So +1 is our new sort of barrier. So to the right of that, we're going to be defined by 2x plus 1. Let's go ahead and set up our t-chart. Our t-chart, x is greater than or equal to 1, so I'm going to choose values that are greater than or equal to 1 just to get an idea of where this thing is going. If I plug in 1, I get 3. If I plug in 2, I get 5. I'm using the top function. And I'm plugging in 3, I get 7. And I plug in this, I get 9. So let's plot those. This is a closed circle because of that equal sign at 1. So 1, 3 is a point. 2, 5 is also a point. 1, 2, 3, 4, and 5. And I ran out of space, but I know that this is linear, so it's going to be just a straight line going that way. And it's not a great line, so I'll try to maybe turn it into a line here. That's a little better. There we go. And I'll put a little arrow on the end because it goes on forever. Alright, the brown one now is defined to the left of +1. So we're going to go 0, -1, -2, maybe even -3. Now let's plot that. Let's get those y values from the bottom section of this. So when x is 0, y is -3. When x is -1, so it's -1 minus 3, so that's -2. And when x is -2, that's -1. When x is -3, that's 0. Now it's also important, as I did in the last one, to figure out the sort of the would-be value at 1. 1 isn't actually in the brown graph, but there's an open circle there. So I'm going to write it down here, and I'm going to remind myself that there's an open circle there, but it's helpful to know that y value. So if I plug in 1 here, I get -1 minus 3 is -4. So I'm going to put all those points on my graph. So 1, -4, 2, 3, 4, open. Again, it's open because there's no equal sign underneath there. 0, -3 is right here. negative 1, negative 2, negative 2, negative 1, negative 3, 0. And just use your straight edge to mark that off. I'm going to change that to a line, see if I can get it to look a little better. There we go. And that should go right down and touch that open circle. And that goes on forever in that direction. Alright, so you can see that this is a function. Right? Open down here, close right above it. And there's a nice barrier right there at x equals 1. So that's the piecewise function. Cool. Again, the domain, this is not continuous. This is a discontinuous function. I think I'm spelling that right. The domain would be all real numbers. There's no break in the domain. There's an issue with the range, though. The range doesn't start until, let's see, 1, 2, 3, 4, negative 4. It's open, so I'm going to use the parenthesis rather than the bracket, and it goes on forever in the up direction. Even though there's a big break here, this arrow is going to hit all the y values that are in between negative 4 and positive 3. And this one, of course, picks up from there, but that will be the range and the domain for that. So there you go. There's a huge gap in between these two. You can really distinctly see the two pieces. Next up. All right, let's use, let's use orange and gray. Orange and gray. Let's go to our first one. I know it's a parabola, so it's quadratic, it's curved, which is kind of interesting. It's defined at 2 and everything bigger than 2. So let's define it at those values. When x is 2, you plug it into the top function. 2 squared is 4, minus 2 is 2. 3 squared is 9, minus 2 is 7. 16 minus 2 is 14, and 23. At 2, 2, it's closed because of that equal sign. So my constraint 2 is right here. 3, 7, 1, 2, 3, 4, 5, 6, 7, and the other ones aren't going to be on the graph. 2, 3, 4, 5, 6. All right, this is a curved function. I know that, so I'm going to just try to do my best to connect that with a curve that goes on forever. Now you can imagine that this graph would, if the constraint weren't there, it would go and kind of go all the way down here. It's a regular parabola shifted down 2 units, so that would be the y-intercept if it didn't have any constraints on it. And that was what I was talking about earlier. There are sort of 2 schools on how to graph these things. That would be like the second school. You would graph the whole thing and then you would erase what you don't need. I don't really like doing it that way. I like doing it this way, where I just sort of build the thing up. I don't have to really do any erasing at all. Alright, so the gray function, the bottom section, is defined when x is less than 2. So that would include 1, 0, negative 1, negative 2. I'm also going to want to define it at 2 just to see where I'm going to put my open circle. So my open circle is at 2. And if I plug 2 into this function, let's see, I get 2 times negative 1/2. So half of 2 is 1, and it's negative 1. So negative 1 plus 4 is positive 3. So that would be the open circle. Let's define it for the other values that are actually on the graph. So when I plug 1 into here, I get, let's see, negative 1/2 plus 4. So that's 3 plus 5. Or 3.5 rather. If I plug in 0, I get 4. If I plug in negative 1, I get, let's see, 4.5. And if I plug in negative 2, I get, let's see, that turns into positive 1, I get 5. So those values are actually on the graph. So I'm going to plot them. I'm going to plot my open circle first. So over 2, up 3, 1, 2, open. 0, 4, 1, 2, 3, 4, and negative 2, 5. Notice I'm not plotting these because it's a little hard to plot half values. Negative 2, comma 5, 1, 2, 3, 4, 5. This is a linear function. I know that because of the exponent right here. So I'm just going to connect these dots the best I can and put an arrow on there. Again, a discontinuous function. There's a lack of continuity right here, the disconnect. Domain is everything, and the range goes from positive to infinity. And we'll do one more. Last one. Triple function here. The triple function is, let's use 3 different colors here. I'll do green for the top, I'll do red, and I'll do blue. So for the green function, it's helpful to have your t-chart. So this is to the left of 0, including 0. So I'm going to go 0, negative 1, negative 2. It's a linear function, so it should be pretty easy to get these points. When x is 0, top function gives me 4 as a y value. This is 5, and this is 6. I know it's closed at 0, comma 4 because of that equal sign right there. So it was 0, 4, 1, 2, 3, 4. It's closed, negative 1, 5, negative 2, 6. It's a linear function. Slope of negative 1 crosses the the y-axis at positive 4. So I'll have to change that to a line here. Put an arrow on it, and I'm good to go. Alright, my next section here, the red section, is defined from 0 to 6, and that means everything that is, you know, the way I think about this sometimes if I'm confused is I kind of black out one side. I say, alright, x is less than or equal to 6, and x has to be bigger than 0. So it's kind of like visually in between 0 and 6, and that's mathematically what it kind of means too. So let's set up our table of values. Our table of values is going to be the easiest way to kind of figure out what points are on this red line. So in between 0 and 6, so that includes 6 because of the equal sign right here. So it's 6. And I don't have to pick all these numbers in between 0 and 6, so let's pick maybe 3 and 1. 6, 3, and 1. It doesn't include 0 because there's no equal sign underneath that symbol, but I am going to want to know that for my open circle. This is where my graph is going to sort of approach or lead towards. So let's do that first. Open circle. When I plug in 0 into the red function, I get negative 1 as my output. If I plug in 6, right here, 2/3 times 6 minus 1. So 2/3 of 6 obviously is 4. 4 minus 1 is 3. If I plug in 3 right here, I get 2/3 of 3, of course, is 2. 2 minus 1 is 1. And lastly, if I plug in 1 right there, I get 2/3 minus 1, which is negative 1/3. Not so easy to plot that one. I probably don't even need to. But I do want to plot the open circle at 0, negative 1. I want to plot 6, 3. 1, 2, 3, 4, 5, 6. 1, 2, 3. And I do also want to plot 3, 1. 1, 2, 3, 1. Alright, so I can see that this has a slope of positive 2. So I'm going 2 up and 3 right. 2 up, 3 right. And of course a y-intercept at negative 1. But that's open. On this side it's closed. You can tell that because of the constraint. Look at the constraint. It's open and closed. Open on the left, closed on the right. So just connect those dots. This one doesn't go on forever, so you gotta kind of do your best. That's not too bad. All right, lastly is the blue section. The blue section goes on forever, and it is defined when x is bigger than 6. So let's set up another t-chart. But you're going to see that this one is actually really easy. So when x is bigger than 6, it's like 7, 8, and 9. Now this one's actually defined as a constant, so it's super easy for these t-charts. Since there's no x here at all, it yields that exact value every single time. Every time. And in fact, when, again, open circle, because the constraint doesn't allow you to get a point when x is equal to 6, but we do kind of want to know what happens when x is equal to 6. This is a constant function, so every y value is -2, but that's open. So I'm going to use my blue pen now. I'm going to go to 6, -2, 1, 2, 3, 4, 5, 6, -2. It's open here and goes to the right. Just like that. So there you go. Sorry about that barking dog outside. But anyway, that concludes my video on piecewise functions. There were a couple of examples there. You know, most of them had just 2 pieces, but this last one had 3. You can also, perform exercises where you're given the graph and you're asked to actually fill in the function rules for each piece. I don't really have time to go into that right now since this video is over 20 minutes already, but as always, just make sure you subscribe. If you have any comments or questions, just type them in the comment section below, and thanks for watching.